For many years, the narrow rocky isles known as Hunga Tonga and Hunga Ha'apai, which were formed by the Hunga Tonga-Hunga Ha'apai volcano, protruded above the waters. An eruption in 2014 created a third island, which was later used to join the other two to form a single landmass. The deserted island at the apex of the summit also gradually developed when the volcano erupted in December as shards of volcanic rock and ash created new land. Hunga Tonga-Hunga Ha'apai is situated in a region of the South Pacific that is teeming with volcanoes, some of which are above the waves and others which are far below, all of which have a propensity for explosive eruptions. City-sized rafts of pumice have been released in the past, and volcanoes have blown themselves apart just to erupt again and create new islands. Due to the Pacific Plate's ongoing submersion of the Australian tectonic plate, there are a great number of volcanoes in the area. The slab's water evaporates as it sinks into the mantle's scorching rocks, rising into the mantle above. These rocks are more prone to melting when exposed to water. As a result, a large amount of magma is produced, which has a propensity to be gas and stick-filled and is a powerful recipe for explosive eruptions. The Hunga volcano triggered the most powerful show of electrical activity ever seen, with hundreds of times the power of an atomic bomb. On January 15, 2022, the underwater caldera close to the tiny kingdom of Tonga unexpectedly reached a fever pitch after weeks of groaning and spewing ash. The Hunga volcano belched 2.3 cubic kilometers of molten lava and evaporated 146 teragrams of water enough to fill 58,000 Olympic swimming pools in the greatest volcanic explosion to occur on the planet in more than a century. More than 1,300 miles away in New Zealand, the sonic boom could be heard, and the shockwave eventually reached the United Kingdom, which is 10,000 miles away. Halfway over the globe, a tsunami shortly followed, much to everyone's distress. Only a few dozen miles to the south of the volcano, it struck Tongatapu, the kingdom's biggest island and location of the capital Nuku'alofa. As the streets started to flood, communications were cut off as people ran for their lives. In the Pacific Northwest, smaller tsunami waves poured across the huge ocean, generating surges in Alaska, Oregon, Washington State, and British Columbia. Stations in California, Mexico, and certain regions of South America also detected small tsunami waves. The resulting plume, a mushroom-shaped cloud of volcanic gases, tephra, bits of magma, and melted seawater, towered 36 miles high, or roughly halfway to space. However, what genuinely alarmed volcanologists, the early readings revealed a massive ring of lightning expanding from the eruption's epicenter at a speed of about 180 miles per hour. Volcanic lightning is well documented. Even Pliny the Younger cites it in his description of Mount Vesuvius' eruption in 79 AD. The primary author of a recent report on the Hunga event, physical volcanologist Alex Van Eaton with the United States Geological Survey, adds that I don't think any of us really expected to ever see a 280-kilometer diameter donut of electrical discharges. The eruption produced an astounding 2,600 lightning strikes per minute at its peak, according to Van Eaton's findings, which was published this month in the journal Geophysical Findings. This makes it the most powerful lightning event ever observed by science. A 1999 thunderstorm in the US Southeast, when NASA recorded 993 flashes per minute, held the previous record with more than twice as many. She and her team also think they've figured out how it happened, which is that plume particles riding a volcanic gravity wave produced the ideal storm for record-breaking lightning. This is based on data compiled from a number of distant monitoring systems, according to Corrado Cimarelli, a volcanologist at the Ludwig Maximilian University of Munich in Germany. Only a small fraction of the world's active volcanoes are directly monitored. Therefore, volcanologists rely on other monitoring networks to gain information about eruptions that are already underway. Luckily, a US weather satellite unexpectedly recorded a bird's-eye view of the Hunga eruption, enabling scientists to chart the eruption's evolution. However, there were only sporadic flashes detected by the satellite's onboard lightning detecting equipment. She'd have to tune into the radio for Venetian to chart the lightning ring. Lightning produces other sounds besides thunder. Sometimes you see its pulse. You see it flicker a couple of times, says Venetian of lightning as it rips across the sky. The source of that pulse is an electron flow through a plasma channel, which generates a strong electromagnetic signal that can be seen as a dazzling flash of visible light and heard thousands of miles distant as radio waves that are audible to humans. In order to depict the location, strength, and timing of more than 200,000 lightning flashes, Venetian and her team methodically combined the data from 3 ground-based lightning detection networks that were able to pick up radio waves from the Hunga eruption. The final count, which Venetian is convinced is an underestimate, registered a pace of almost 2,600 flashes per minute at the peak of the ring's intensity. Eric Bruning, a professor of atmospheric science at Texas Tech University who was not involved in the study, said that this is a genuinely astounding amount. According to Bruning, a typical low-end thunderstorm could have a lightning strike every minute. There will be hundreds of flashes per minute in large supercell thunderstorm type that produce tornadoes, a magnitude bigger amount of lightning struck during the Hunga eruption. The geographical information adds even another distinction to the Hunga event. Lightning was observed at altitudes that were miles above what was previously believed to be feasible. Researchers attribute this to the massive injection of hot sea water into the atmosphere. Gravity waves, which happen when a trigger, like a volcanic plume, forces air upward or downward, are another peculiar aspect of the Hunga eruption. A volcanic plume is made up of extremely hot volcanic gases, debris, and evaporated water. These waves might be more buoyant than the air around them, which would result in separate layers like water and oil. When an object reaches its maximum height, it would normally fall straight down. But in this instance, the plume is stuck above the layer of regular atmosphere. So as it descends, gravity forces the plume out horizontally, producing waves like ripples in a pond. Tephra fragments and salt water vapor are riding the gravity wave. The water vapor rapidly cools as it ascends up into the atmosphere, generating ice crystals and graupel, which are tiny pellets of soft hail. According to Bruning, as the ice fragments scrape past one another, static builds up, generating water basically electrically charged dipping dots. Normal thunderstorms produce lightning through the same ice charging method. Volcanic eruptions add the special ingredient of silicate charging because tephra creates its own charge through related process. According to Venetian and her team, the leading edge of a gravity wave would be ideal for producing lightning. By separating particles by size, the wave's sharp edge may cause denser particles like graupel or tephra to slide down the wave's edge like surfers, while ash and tiny ice crystals may glide upward. Thus, the conditions are created for lightning to balance the charge in clearly defined zones. The study's authors, according to Bruning, have developed a compelling physical explanation for a puzzling phenomena that had both volcanologists and meteorologists scratching their heads. There are still a ton of mysteries, though. Venetian notes that there is a point where the lightning ring seems to vanish, but then the donut hole fills back up with hundreds of flashes. According to Venetian, we don't have any answers for the donut hole. That will likely take 5 PhDs to do. Tracking volcanic lightning, according to researchers, could be a useful technique for no-casting eruptions, with the potential to have life-saving effects. That dense plume makes it difficult for satellites to determine whether an eruption has reached its peak or whether additional jets of lava are continuously erupting during volcanic activity. To help with evacuations and public health decisions, scientists can use real-time data as they get more knowledge about how volcanic lightning develops, according to Chimorelli. In fact, Lightning frequency can indicate the arrival of a new jet. Van Eaton continues by saying that volcanic ash poses a threat to nearby populations and aircraft. Any tools we can bring to bear for earlier detection, for rapid characterization of what's happening that could impact airspace and people. And that ends today's episode. Please subscribe to Weather Collapse if you want to know more and be updated on the latest news about natural calamities or disasters happening all over the world. And don't forget to like today's video. We'll see you in the next video. Thanks for watching.